Today we're going to talk about probability and Venn diagrams, and hopefully this is going to be quick because it's a super easy topic, but I do see some people drowning in formulas trying to solve questions that are really very simple. But I've talked about this before in different videos. Formulas, they do have a place because sometimes they simplify the situation, but for a situation that is already incredibly simple, I just don't feel that there's a need. The formulas will be just describing the situation, but I would rather understand the situation. Okay, so let's go. There's two circles here. One of them's called A and the other one's called B, but the circles sort of overlap on the page so that it makes for four different places, like 1, 2, 3, 4. And the first way in which I see sometimes people mess this up is by believing that the A part, the part that has the name, is just this fourth part, but it's not. A is the whole circle, like this. Everybody that is inside of the circle is A, so 2 of the parts belong to A, and 2 of the parts belong to B. Now, maybe you've noticed that this part belongs to both of them, and that's what is called the intersection of A and B. The symbol for intersection is this upside down U, and it's just one of the 4 parts in the Venn diagram. But if you look at everything that is not white right now, there's 1, 2, and 3 parts that are painted in some color. That's the union of A and B. The symbol for union is just the regular U. So the intersection was the one part that belonged to both of them at the same time, and the union is the 3 parts that belong to at least one of them. Is the intersection part of the union? Yes, because it belongs to both, so that is at least one. But this is also part of the union, that is also part of the union. So it's 3 parts for a union, 1 part for an intersection, and 2 parts for just a single one of the sets. Now we should talk about complements. The complement of a set is everything that is not in that set. So if A was 2 parts, the complement of A is going to be the other 2 parts. Like this, the purple here is the complement of A, and you'll see that if I put the A set back in here, now all 4 parts are painted and nothing is overlapping. So the orange one is A, the purple is the complement of A, and when you put the set together with his complement, you get everything. In other words, the union of A with complement of A has probability 1, which is 100% everything. But the intersection of A and complement of A is nothing. There is no intersection. Nothing is overlapping. So the intersection between A and its complement is 0. B also has a complement, which is everybody that is not inside of B. I could say for B and complement of B all of the same things that I said about A and complement of A, but it's more interesting when you put them together like this. So now there is an overlap. There is one of the 4 regions is overlapping, which is the one outside of both circles. That is the intersection of A complement and B complement. In other words, everything that is not in A and also not in B, so that's the outside. But as you can see, there's also a union. All the parts that are painted in some color now, everything that is not white, so that is 3 parts of the Venn diagram. Like we mentioned, an intersection is 1 part and an union is 3 parts. So now all of these 3 parts that are painted is the union of A complement and B complement. You can overlap any 2 of these things and make interesting sets. My next example is going to be the set A and the set complement of B. When I put them together, they have one of the 4 parts of the Venn diagram that is an intersection. It's this moon-shaped one here that is looking kind of red, but it's actually just orange on top of purple. So that region over there, the one part of the Venn diagram that I said in the beginning that sometimes people mistake for just being A, that's not A. That's the intersection of A with B complement. So it's everybody that is inside of A and at the same time outside of B. But if you look at the union right now, the union should be 3 parts, right? 1, 2, and 3. Everything except for this white moon right now. All of these 3 parts together are the union of A with B complement. We can also do it the other way around. So the darker looking moon on the right here is the intersection. It is darker because it is overlapping 2 colors. That shape is the intersection of B and the complement of A. And everything that is currently some color in this picture is 3 out of the 4 regions in the Venn diagram. that is the union of set B with the complement of set A. So there are formulas. The formulas describe these relationships between the sets. For example, the probability of the union, which is the whole area of the three painted regions right now. So you should start with the area of one of them, like the area of B here, and then you should add the area of A. But the area of A is adding this part again, right? Because that part is in both of them. So if you just want to get the full area of the picture here, you have to subtract that middle part just to prevent it from being added twice. And that's why the formula looks the way that it does, that the probability of the union is the probability of one of them plus the probability of the other minus the probability of the intersection, which is the area of this middle shape here. And then there's a whole category of questions that is very common. It appears a lot, and it's all the same question with variations on the theme. And that's when I see people kind of drowning in formulas unnecessarily. All of these questions can be solved by just putting numbers in a diagram. So let's see an example. This kind of question will always give you three things and ask for one thing. He has to give you three things because there are four parts in the diagram. So he will give you three numbers and you can figure out the fourth one according to the fact that the sum of all four of them needs to be 1, which is 100%. But a lot of times, like in this example, one of the things that he's giving you is the intersection. The intersection of A and B is 0.55. So you can start there. You can put the 0.55 in the intersection. It wouldn't be as easy to start with P of A equals 0.7, for example, because 0.7 is P of A and A is two parts of the diagram. The intersection is just one part, so you just put a number in one part. It is more difficult to put one number in two parts. You want to put one number in one part. But now you can do that because in order to get to 0.7 for P of A, you already have 55 here, so the other 15 have to be there. Now we can do the same thing for B because the P of B is 0.75 and it is both of these regions. So 55 plus 0.2 is going to give me the 75 that I want. I could use all that right now to figure out the fourth number outside, but I'm not going to do that just yet because I see that part A of the question is just asking me for the probability of A union B, and I already have that. A union B is all three of these regions put together, like that. So what I have to do right now is to just add all of those three numbers. So the answer for part A of the question is 0.9, which, by the way, is exactly the thing that I'm going to use to figure out the number that goes out here in the fourth place, which is 0.1, because 0.1 plus 0.9 is 1. That has to be everything. And now that my Venn diagram is complete, I can read off of it anything that I want, including what part B is asking me for, which is the intersection of both of the complements. A complement, intersection, B complement. So it's this one and this one. It's an intersection, so it's the overlapping part. It's the one that is colored in both colors. Not this one, not this one. It only has one color. This one also has just one color, but that one has both, which is the 0.1. It was the last number that we included in the diagram. This strategy is going to solve all of the questions in this category, okay? So for our second example, he did not give me the intersection of two sets as one of the three things that he's giving me. So he gave me P of A and P of B. Both of those are two parts of the diagram. I don't want to handle that. And he also gave me P of a union. A union B is 0.6. I'm going to start by working with that one because A union B is three parts, which means that the fourth part is whatever is left to make 1. So if A union B, all this colored part here is 0.6, that means that outside we have a 0.4. He also said that the probability of A is 0.5. So outside of A, I'm going to need the other 0.5. But outside of A, I already have the 0.4. But in order to reach 0.5 outside of A, I still need 0.1. So that needs to be here. So the third piece of information that the question gives me is that the probability of B is 0.4. I already have a 0.1, so I'm going to put the other 0.3 over here. And now he didn't give me anything else, but I don't need anything else because I already know that all four parts added together is 1. So now I need 0.2 there in the last one. And now that my Venn diagram is completed with all of the information that was given in the question, I can answer any question that he asks. In this case, he is asking me for the probability of A given B. That is a conditional probability. And it is the one exception that I'm going to make for the use of formulas in this type of problem. And it's in the booklet, so please don't mess up this formula. Now there are two things that I need to read off of the diagram in order to put in the formula. It's the intersection of A and B, and it's the probability of B itself. Probability of B is 0.4, and the intersection is 0.3. So you put both of those numbers in the formula and then just finish the calculation. The next question is extremely similar, so pause the video and try to solve it before I do. I am going to start with the union again for the same reason as in the previous one, because A is 2 parts, B is 2 parts, so that's difficult to put in the picture. But the union is 3 parts, so that tells me something about the fourth part. If the union of A and B is 0.8, then out here is 0.2. I know that P of A is 0.45, so outside of A I need 55. I already have 2, so I need another 35 for here. Probability of B is 65, so with 35 here I need 0.3 in the middle. And it's going to be 0.15 to finish the diagram with everything adding up to 1. And like I was saying, once you've done this, you can read any information that you want from the diagram. This question is going to ask me for a slightly different information than the previous question, but he does start by just asking the intersection of A and B, which is this one in the middle, which is 0.3. And now he wants a conditional probability again, but instead of P of A given B like in the other question, now it's P of A complement given B complement. It is the same formula as before, but of course I have substituted different letters. And now I need to read these two things from the diagram. First of all, the probability of B complement for the denominator, I don't even need the diagram for, because the probability of B was something that he gave me in the question, which was 65, so the complement of that needs to be 35. But if you want to check in the diagram, here it is. The pink one is B complement, and we can see it's 0.2 plus 0.15. Now the other one that we need here is the intersection of both of the complements, right? So A complement intersection B complement is this. Is the intersection is the overlapping part. So not this, not this. This would be the union, but the intersection is just the outside part that is getting both colors right now. And that part has a 0.2 as a number. So you plug that into the formula and finish the calculation. Question 4 is slightly different because one of the things that he's giving me is a conditional probability. That didn't happen in the previous 3 questions. But still, he is giving me 3 things. That's what I told you in the beginning of the video, that can't change. It has to be 3 things. But I'm not going to start by worrying about what do I do with the conditional that was given to me. Instead, I'm going to start with the union like I've been doing, because the complement of 0.55 is 0.45. That's what I'm going to put outside. So that's a strategy that is even more general than just the category of problems that we're talking about today. Don't worry initially about the things that you don't know what to do with. Just do the things that you know how to do. For example, the probability of A here is 0.4, which means that outside of A, the complement of A needs to be 0.6, and it already has a 45, so I'm going to put 15 here. This is exactly what I've been doing in the other questions, and I really am going to have to handle that conditional. It's the probability of A given B. So I am going to need the intersection and the probability of B. I don't have either one of those things, but if I called this one X, which is the intersection, now the probability of B is automatically X plus 0.15. You put that into the formula and it needs to be equal to the 0.25 that was given as the conditional probability. And now you just solve this equation. Knowing how to solve equations is the most important skill that you need to have to be successful in any math course, but it's not what this video is about, so I'm not going to go through the solving of the equation. Just mention that in the end I found the value of X, but the question was the probability of B. And we had talked before about how the probability of B, you need to add 0.15, so that's what I did, and the answer here is 0.2. Question number 5 is giving me two intersections. That's really good. That's two numbers that are going to go straight into the diagram, but I need to be careful not to mess up which places they are. One of them is A intersection with B complement. So it's that one. That's where the 016 goes. And the other one's talking about A complement intersect B, which is outside of A and inside of B. So it's this one. This question is telling me where to put the X, so I didn't have to think of that like I did in the previous question. And the third piece of information that he's giving me, because it always has to be 3, in this case, the third piece is the fact that A and B are independent events. Independent events is the only time when you get to say that the probability of the intersection is P of A times P of B. This is in the formula booklet, although a lot of people still get it wrong by applying this when the events are not independent. But in this case, they are. So I am just going to substitute things into here and calculate. P of A intersect B was X that he told me before. And the probability of A and the probability of B, I'm going to go look in the diagram. So A is 016 plus X, and B is 036 plus X. So that's all in the formula now. I'm just going to go and solve the equation. Okay, so this one was a lot more annoying to solve because it turned into a quadratic, but this was a paper 2 question, so I just used my calculator and everything was fine. In this case, the quadratic only had one solution because both solutions were the same. But sometimes in this kind of problem, what will happen is that you will get two different values of X, and one of them will not make any sense in the context, as it is going to be a negative number, which a probability can't be, or it's going to be a number that's bigger than 1, which a probability also can't be. So then you choose between the two solutions of the quadratic, the one that makes sense for the problem. But in this case, it was just the 0.24. So I put the 0.24 there where the X used to be. And now I'm going to figure out what number goes in the fourth part of the diagram to add everything up to 1. What a coincidence! It's another 0.24. But now I can use this diagram to read the things that I need for the question that is being asked, which is, again, the conditional probability of A complement given B complement. It's the same as the one that was in the previous question, but now it's going to be different numbers. So we need the probability of the intersection of the complements and just the complement of B. The complement of B is 0.4. And the intersection of the complements is the outside part, which is 0.24. So you just plug those in there and finish the calculation. Finally, the last question that I'm going to solve today, question 6, also is dealing with independent events. He's giving me information in a more creative way than usual by saying that the P of A is 3 times the probability of B. But he does give me one number, which is where I'm going to start. So the union of A and B is 0.68, which again means that the outside needs to be 0.32. But then if I was going to follow the same strategy that I was doing before, I would need to choose a place to put an X. And it feels to me like the middle is the most appropriate place. But wherever you do choose to put it, you don't have enough information to keep filling in the diagram. This question is different. It is more abstract. It has fewer numbers. So I think that this is the adequate place to actually work blindly with formulas. This is why formulas exist, is to help us handle situations when we can't concretely look at them. It doesn't mean that we never should look at things. We absolutely should. I'm going to work blind for this question because there is no way to do it by looking at the diagram. So I just wrote down the things that the question gave me. The events are independent, so the intersection is the product, and then I substituted PA for 3PB, which he also gave me. I wrote the formula for the union with the subtraction of the intersection, because by now I've solved enough of these questions that I actually know what this formula is saying. I'm not really blind anymore. And then I substituted things into it. The number that he gave me for the union, 3PB in place of P of A, and the thing that came from the top line into the intersection. Now it's just an equation in PB. Let's solve it. Again, I used my calculator for this quadratic, and in this case, I chose the answer 0.2 because the other value was bigger than 1. So here's the thing. I've just finished solving this difficult question by writing a bunch of formulas and plugging in numbers, and I didn't draw a single picture. And I can imagine that there are people watching this who are going, but this is what I want to do in every question. Then why did it take you so long to finally solve a problem in the way that I want to do them? And yes, you could totally have solved all of these questions, including the first one, which was the easiest one, by just copying down formulas from the booklet and then plugging in numbers for variables. And I'm not trying to convince you that that strategy is not valid, but the thing is that a lot of people ask me, a lot of people say that when I solve the questions, when they see me solving the question, everything looks easy. But for them, it feels difficult. So how can we bridge this gap? It's a thing about teach me how you think. And I am trying. I am trying to teach you how I think. This is the way that I think. I do think that most questions are easy. That's maybe why it feels like they were easy when you see me doing them, because I do feel like they are easy. But I am not trying to do this to the questions. This is what I do with difficult questions. And if you treat every single question as a difficult question, I wouldn't be surprised if you find them all difficult. So it's a kind of a contradictory thing. People do ask me to tell them how I'm thinking about things that makes it feel so easy for me. But on the other hand, when I say how I'm thinking, there's always somebody who will answer by asking, but do I really have to do it this way? Can't I do it in another way? Can't I do it with formulas? Well, sure, of course you can. The formulas have been designed to always work. But I still like to share with people the other ways in which I'm thinking about these math problems, which is not always the use of formulas, because I do feel very strongly that in a lot of times there are easier ways to do things.